So we know that the general formalism of Bronsted-Lowry acids and bases are that acids donate protons and bases accept them. And the generic representation of that reaction looks like this. So you have HA plus B, that B accepts it, becomes BH plus, and the HA dumps it, which becomes A minus. And so we have the acid and the base under this model. But this is sort of a constraining view of acids and bases because there are many examples of compounds and chemicals that can contribute acid or basic character to a solution without necessarily explicitly transferring proton. So that necessitates a sort of different convention of thinking of acids and bases, which is called Lewis acids and bases. So Lewis's acids and bases don't use protons to necessarily categorize acids and bases. They use electrons, which results in the same categorization of acids and bases that you would for Bronsted-Lowry, but it opens up the options to things that don't necessarily include a proton. First example includes protons. So this could be easily thought of in Bronsted-Lowry or Lewis acids and bases, but it's a simple example. And so a Lewis acid is anything that is an electron pair acceptor, and a base is an electron pair donor. So if we look at this system, which we've thought about actually quite a bit already in this class, we have ammonia, NH3, and I'm just drawing it out as a Lewis structure so you can see explicitly where those electron pairs are. And remember, a base is an electron pair donor. And so if we look at this pair, if we think about what's going to happen here, we've got an acid and we've got a base, right? And that pair is going to grab that proton, and that is going to look like, let's see if I can draw that out here. That's going to look like this. So here's our arrow pushing, and that's going to produce the NH4 plus ammonium ion. And so if we look at how that's defined in Lewis conditions, in this case, we have an acid. That's an electron pair acceptor. That's exactly what happened to this proton, right? It had no electrons to begin with. Now it's bound here. The electrons are these two here. It accepted those. And similarly, this base is the electron pair donor. So often Lewis bases have this lone electron pair that can easily be donated to something that is electrophilic, something that wants negativity. So that means positive things like protons. We can similarly use this Lewis acid base convention to rationalize the acidity of the aluminum ion that we talked about in a previous video. So here we have this positive aluminum ion. We have it reacting with water. The lone pairs on water are then the things that get donated. So under the Lewis convention, we would consider water a base. It's donating that electron pair. And similarly, aluminum ion itself is accepting those pairs to form this new bond here, and we call that a Lewis acid as the electron pair acceptor. So we already sort of walk through the consequence of this, the fact that it's going to form hydronium ions and it's going to make an acidic solution. But now under this Lewis formalism, it's really clear because aluminum is acting as an acid, but it doesn't explicitly look like HA, what we'd seen before. And so that's the utility in Lewis acid convention over the Bronsted-Lowry convention. So another example here is the copper ion. This is a metal ion. This is acting as an acid, but it's not reacting in water. So this is really demonstrating the utility of the Lewis acid-base convention because it's going to react to form this complex where we have 4 ammonias forming around copper, very similar to what we had happen when we had aluminum in water. The only change here is instead of the lone pairs on a water molecule, we're using the lone pairs of the ammonia and donating them to this positive ion. But the same thing is true. This is our Lewis base. Here's our Lewis acid. And that fits even better, this convention, because we're not in water. And so pH is not really a defined characteristic because we don't have hydronium ions that are forming. So we can't really say it's acidic or basic simply by measuring the pH. But we can generally say this is a Lewis acid because it's accepting those electron pairs.